Thanks for the opportunity to talk here. Today I'm going to talk about some relation between like a Markov chains, especially random walks, and the algebra like monoid. Okay, so this is a joint work with Sahil and the team in Monash University, and Sahil is the honest, or is the honor a student who did honor project with us. Okay, so let me first begin with some definitions. So it's very simple. A semigroup is a set of S which is closed under an associative operation denoted by this dot, which means for all element xy in S, then S dot y is also in S. It's closed. And a semigroup is called a monoid if it contains an identity element. What is identity element? It means that for any element S, also for any element x dot I equal to I dot x equal to x. That's the identity. Let's look at a very simple example. A set of these numbers 0, 1, 2 to n minus 1 is a monoid with the operation is addition modulo n. That's quite obvious. And the identity element here is just 0. Now let's look at a slightly complicated example, which is big omega. It's a set of its binary 2 bits. Like it has 4 elements in this set: 0, 0, 0, 1, 1, 1, and 1, 0. Okay, so if you draw it here, it's a square like a square lattice. So now define 2 mappings from omega to itself, or the F1 and F2. F1 is the one flip the first bit. F2 is the one flip the second bit. For example, if we start from 0, 0, we apply F2, which means flip the second bit, then we'll get 1, 0. If we are now 0, 1, sorry. If we now here we do F1, which means we flip the first bit, then we get 1, 1. Okay, that's quite easy. And you can see is F1, F2, they can generate a monoid. It's MF having these 4 elements here, and the operation is just the function composition. Okay. Now, if we choose a sequence of elements in this monoid MF and then act on this omega, then it corresponds to a walk on this 2-dimensional cube, right? Or moreover, if we assign a probability distribution P to the monoid, then we choose elements in this monoid according to P, then act on omega, then what we can get? We get a random walk. For example, if we give probability half to F1 and F2, then it is a simple random walk. We just do simple random walk here. If we give probability half to the identity and the probability quarter to F1, F2, then it is a lazy random walk, which means each step we have half probability to stay still and then half probability to move. Okay, so then is this the only monoid corresponding to that random walk? The answer is no. There's another monoid. So let's look at this example. This is a monoid. So for I in 1 or 2, define this function Fia from omega to itself by updating the state of the I bit to A. So before the F1, F2 just flip, now Fia is update the I bit to A. Of course, it's binary, so A is 0 or 1. So we update the state of I bit regardless of the previous state of the I bit. We just update to A. So now the set of this Fia also generates a monoid. Now, if we assign a uniform distribution to this functions Fia, we have 4 of them. You can see because A can be 0 or 1, I can be 1 or 2. So we have 4 of them. If you assign uniform distribution to that, you can check the random walk. In the induced random walk is also a lazy random walk on the 2-dimensional hypercube. We have 2 monoids correspond to this random walk, and it's not very hard to generalize to this very general case. Like instead of 2 bits, we can have n bits. So 2 bits is a 2-dimensional cube. The n bits will be this n-dimensional hypercube. And instead of binary, we can generate 2, let's say, Q colors. Q colors means that the A is not 0 and 1, but it can be 0, 1, 2, up to Q minus 1. And we can we can consider a very arbitrary distribution P on this monoid. So now, so this will correspond to a very general and also non-local, because it can jump from one place to any other place, random walk on this n-dimensional hypercube. And we are very interested to study the spectrum of the transition matrix. And the spectrum of the transition matrix is very useful in Markov chains because it tells lots of information, like the mixing time, like how much time you need to reach the stationary distribution, something like that. Okay, so the method the main method we are going to use to study the spectrum is the Brown theorem. So the Brown theorem only applies to a very special monoid. It's called a left regular band. So a monoid is called a left regular band if its elements satisfy like f squared equal to f and fgf equal to fg for all elements f and g. Here is just a function composition. Their operations are function composition. And you can easily check the second monoid mu is a left regular band. Just updating one, not the first monoid which flips. The first one is not a left regular band, but the second one is. So if it is a left regular band, then let's define this MF to be the set of elements in monoid times F, and we call it the principal left ideal generated by F, and you can let it lambda M to be the set of these ideals. Okay, so with this, we can basically, Brown theorem tells us that each for this induced random walk, a very general case, each ideal X can contribute an eigenvalue lambda X, which is equal to this. So here I just sum over all elements in the monoid such that the generated ideal is bigger than X. Here this MF and X, there are two sets. Bigger than means that X is a subset of this. And here is just a probability of F. So we just use this theorem, and we can, after a bunch of calculation, we can apply this to our case, to this, Sorry. So here the Brown theorem is a theorem which applies to any left regular band, like any monoid and any state space omega. Here we can apply this to our case. We'll consider this general random walk on n-dimensional hypercube. Now we can obtain the eigenvalues. Let's say this is the eigenvalues lambda s. So s is just a subset of this 1, 2, 3 to n, and in the summation we just sum over all subset of s, and the p of s is the probability of fs prime, and also a probability of s prime is just this. We sum over all state in the it's q is a color, q to the power of s prime is inside is the probability of s of these elements. So we get a very simple result for this general non-local random walk on the n-dimensional hypercube. Okay, so let me conclude this. So basically, I think maybe the message I want you can take home is that like each Markov chain, it has a monoid representation. So studying the structure of the monoids can help to understand the properties of some Markov chains. Not all Markov chains, but some. For example, here it's the left regular band. Such for properties means such as the eigenvalues and their multiplicity. We can also know the multiplicity of these eigenvalues. We can also know the eigenspaces sometimes. So yeah, basically, if you are interested in this topic, here's some references you can look at. Okay, that's my talk. Thank you very much.